Hi everyone, my name is Hassan. Today I'll be presenting our work on metamorphic testing of action policies. Okay, let's get started. Our work is titled as Metamorphic Relations via Relaxations. In this work, we developed an approach to obtain oracles for testing action policies. This is a joint work with my PhD advisor, Maria Christakis, and 3 other collaborators. As you all may know, action policies represented by neural networks are highly successful in many complex sequential decision-making problems, such as robot planning or game playing. Traditionally, once the policy has been learned, we feed it with a state to obtain next predicted action. However, in some safety-critical domains, mispredictions, or speaking from the software engineering perspective, bugs in an action policy might result in severe consequences. For this reason, action policies has to be characterized by high degree of dependability before they go into production. And testing is a natural paradigm to address these concerns. But first of all, the question is, what is a bug in an action policy exactly? A natural answer to this question is that satisfying a failure condition. For example, losing the game, crashing into other cars, or in general, satisfying any failure condition in any environment. But what if the failure is unavoidable? Can we blame the policy in this case? Of course, no, because if the failure is unavoidable, then the policy is not responsible from this failure. So we cannot identify such situations as bugs. We could ask the optimal policy whether the failure was unavoidable or avoidable. However, as you may guess, calculating the optimal policy is not tractable in many cases. This is somewhat similar to the oracle problem in software testing. The question in oracle problem in software testing is that, let's say we have a test input, and what would be the expected output of the program under test? So we have a test input out at our hand, and if we have a program under test, we need to know the expected output of the program under test to utilize the test input that we have at our hand. Among the many solutions, metamorphic testing is one of the most popular ones, for oracle problem. According to it, we have a metamorphic relation over inputs and the corresponding necessary relation over the outputs. For example, consider inputs I1 and I2, which satisfies the metamorphic relation over the inputs. And let's say we have a program P, which is the program under test. Once we feed it with the I1, we obtain O1, the output. And once we feed it with I2, we obtain O2. And according to metamorphic testing procedure, we check whether O1 and O2 satisfy the output relation or not. If not, then we simply say that there's a bug in the program P. More concretely, let's consider the autonomous vehicles, where the input is the weather condition and the output is the predicted speed. Let's say we have two weather conditions where the one is sunny and the other one is rainy, and we expect the speed to be 25% lower in the rainy condition. If not, then we say that there's a bug in the policy of the autonomous vehicle. So this is how we handle the oracle problem in software testing in general. However, how do we combine the metamorphic relations in general sequential decision-making problems? For this, we benefit from the widely studied concept called relaxations in planning community. According to it, assume we have states S and T, which are related in terms of relaxation relation, which says that T is easier to solve than S. So if we have this relation between the two states, then we can simply say that if the policy pi is failing on easier state T, but not on harder state S, then we know that policy pi contains a bug manifested on T. So if you know this, then we can use the relaxations as a means to specify metamorphic relations and also to obtain oracles. In this work, we focus on state relaxations. For example, if let's say in the environment, if the obstacles need to be avoided, we can remove the obstacles. If the resources are limited, we can increase resource availability, or if there are time constraints, we can postpone deadline, and so on. So in this work, we consider manual relaxation design. However, as you may notice, relaxations are decided in very high level, so there's almost no domain knowledge is required. So let's go over the more concrete relaxations that we considered in this work. So we considered several case studies. The first one is called highway, where the task is to reach the end in a two-lane street with a traffic. And we relax this state by removing a car in the street. Let's say if this is the state S, where our agent is the red car, we can simply remove one of the cars and then one of the other cars and obtain the relaxed state T. So if the policy is able to solve the state S, but not able to solve state T, then we can simply say that the policy pi contains a bug manifested on state T. And the next is called lunar lander, which is a gym and OpenAI gym environment where the task is to land the agent on its legs. We simply relax this state by decreasing the height of the landing pad. So if this is the state S, this is the relaxed state T, where the agent has more time and space to balance to keep the balance. So if the policy is able to solve the state S but not state T, then it contains a bug. The next is bipedal walker, which is again an OpenAI gym environment, and the task is to move a bipedal robot forward till the end of the terrain. And we relax the state by making the terrain smoother. If this is the state S, where the terrain is a bit, if you see rougher, we make it smoother to relax it. So this oracle idea is only a part of a larger policy testing framework that we developed in this work, and this policy testing framework is called as PyFuzz. It consists of two main components called fuzzer and oracle. The fuzzer is responsible for generating a diverse set of pool states, on which the policy to be tested, and oracle utilizes these diverse set of states to identify the bugs in the policy. So PyFuzz is implemented as a generic policy tester. So it is independent of any specific environment. So you can simply add a new environment and a policy to test. It's also publicly available at GitHub in this link. I encourage you to go download and play with it. So next, let's consider with the evaluation highlights. So in this, here you see 3 plots, where one for each case study, where we report the number of bugs over the pool size. So here we compare the metamorphic oracle that we developed with the other oracles. The first oracle is called the fail oracle, which is shown with the orange color. The fail oracle simply flags a bug whenever the policy fails. So it doesn't care whether the state was the failure was avoidable or unavoidable. So the blue line is called perfect oracle, which we have only for the highway. For lunar lander and bipedal walker, calculating the perfect oracle is not tractable. So we show the metamorphic oracle with the red line, and we also develop a heuristic oracle with simple rules, which also represents the closest related work. So according to it, if you see the plot for the highway, metamorphic oracle and the perfect oracle are almost indistinguishable. Fail oracle, as you may guess, fail oracle flags many bugs, flags many unavoidable failures as bugs, and heuristic oracle misses many of the actual bugs. So for lunar lander and bipedal walker, this is also the case. So we say that metamorphic oracle is highly useful for identifying bugs in action policies because it's superior to the heuristic-based and failure-based alternatives, and it's very close to the perfect oracles. So in conclusion, testing, so we need to, so the action policies has to be characterized by high degree of dependability. So we need them to be tested thoroughly. And testing them requires smart oracles because the dummy ones are not capable of doing this, capable of doing this. So we have shown that we can obtain a very, very successful oracle by adapting the idea of relaxations and using the metamorphic testing procedure. So in the future, we want to automate the design of state relaxations, and we want to close the loop with the retraining by feeding the bug states back into the RL procedure. So this concludes my talk. I would be happy to take any questions. Thank you for listening to me.